Good afternoon. My name is Alejandro Delgado, and this is my black hole coding lab. Black holes are phenomena that occur in our universe that have so much gravitational force that not even light can escape. Therefore, to escape a black hole, you'd have to go faster than the speed of light. Not possible. Due to net force, however, it is possible to create a trajectory where a spaceship can escape the pull from a black hole. In this lab, I experimentally determined the mass of a black hole through a computational model on GlowScript Python. Part 1 entailed calculating the mass of a black hole through the analysis of net force on a star experiencing the pull from a black hole. Part 2 entailed calculating the initial velocity needed for a spaceship to fly by the black hole, but escape without crashing into it. Some foundational physics knowledge we need to know before conducting this experiment is that Fnet in the parallel direction is equal to the change in momentum in the parallel direction, which is just the change in velocity times m over the change in time. Fnet in the perpendicular direction, on the other hand, is the change in momentum in the perpendicular direction, which is also equal in this case to the gravitational force coming from the black hole. The escape velocity is the minimum velocity needed to escape the gravitational pull, and the Fnet is the sum of all the forces acting on an object. So for part 1, I began my calculations by by finding the initial momentum and the final momentum, and also and delta V and delta P, which is going to get us delta P over delta T, which is equal to the F net, the sum of all forces on the black hole and on the spaceship and on the star. However, in order to calculate each component, we're going to need to know P hat, the magnitude of dp dt, and dp dt parallel, so we could add these components together. Once the dp dt perpendicular and dp dt parallel components are added together, we can find F net, which is just equal to dp dt. In order to calculate the mass now, we can set the equation equal to F net is equal to gmm over r squared to find the mass of the black hole, which is exactly what I did here in this program. And we found that the mass of the black hole is 9.44624 times 10 to the 33. The change in momentum has more to do with the effect of forces over the change in time. However, the net force has to do with the sum of all forces acting on an object in a given time. However, these are related in the sense that the change in momentum divided by the change in time is the net force. In other words, the derivative. For part 2 of this experiment, I first had to find the force of the black hole on the ship and the force of the planet on the ship to see how the ship would change its trajectory as it was moving. F net on the ship is the sum of both of these forces. However, we also have to find F net on the planet to see how the planet would move in its trajectory and how that would affect the spaceship. So we have to find FBH on planet, which is just the force of the black hole on the planet, and the force of the ship on the planet. And these forces added together will get us F net on the planet, giving us the trajectory of the planet. In order to find the planet velocity and planet position, as well as the ship velocity and the ship position, we have to use the velocity update formula, which is v initial plus F net over m times delta t, as well as the ship position, which is the initial position times the ship velocity times delta t. As you can see here, here is the trajectory of the spaceship as it goes around the orbit. It gets close enough to the black hole where it can do a little flyby, but it's not going to crash into it. Here I have to calculate the initial velocity simply by doing trial and error to see how to get it to go around the black hole, but not crash into it. But what if we wanted to orbit? In that case, we would have to significantly lower the y component of the velocity, making it do a complete orbit revolution around the black hole.